Unchecked data growth and data sprawl are having a profound impact on life science workflows. As data volumes continue to grow, researchers and IT leaders face increasingly difficult decisions about how to manage this data while keeping the storage budget in check. Stay tuned and learn how these challenges can be overcome through the use of object storage and biomedical workflows. In this InfoCast, we'll hear one of San Diego Supercomputer Center's distinguished staff discuss how object storage enables big data applications, distillation of medical image data for biomedical action, and real-world data challenges in identifying gaps in multi-scale modeling capabilities to develop new methods and tools to bridge these gaps. And now, it is our pleasure to introduce Ilkay Altintas, SDSC's Chief Data Science Officer and Workflows for Data Science Director.
So I'd like to talk about first what we mean when we talk about storage for big data. Right? Let's try to look at traditional, ways of organizing files in the file systems. It's more structured, and it's not a practical mode of storing for big data workloads when we talk about volume, variety, velocity of the data, pushing for alternative or more innovative ways of doing processing, loading, analyzing data. So in a way, object stores have been used as an answer to gap that need, and where each data is stored as a binary object, almost like a blob, with metadata attached to it, so users can find it with the metadata. And applications, when they read it, they can actually add a schema or some model on top of it and use it for their need. This is like nothing that you haven't heard in the cloud domains, right? The cloud storage does that, but I think having a storage with an active access like this brings also the concept of private data. Being able to securely have it in a private data archive. So in Hadoop-based data architectures, then you will sort of load the data into HDFS and process it from there. But you can imagine data being available to an HPC system and being analyzed just like a regular HPC workload. But then your storage is more active than traditionally having to load it separately. Often, as you know, in streaming where this gets referred to as data lakes, but it can be thought of as a standing archive. So if we talk about medical imaging here, actually, or biomedical imaging, I should say, the idea is to get the data and get as much knowledge as we can from that and turn it into an action, right? That's sort of the data science promise. So how do you take the data sort of in this raw image space that requires a lot of analytical processing power or sometimes optimized use of HPC and push it to a form that you're actually bringing to what I call a high value zone in a way. You're adding metrics to it, you're adding metadata to it, and you're making it available to a number of communities and opportunities or interfaces. You can even load the data in a reduced form if you can access to it with all the structures and everything that David was referring to from a mobile device even. So you're, in a way, by adding the structure on top of the raw data, you're adding an amplified value to it without even analyzing the data yet, in a way. This is an approach we use in National Biomedical Computation Resource. The goal or the objective of the NBCR resource, I should say. It's a project funded as a P41 from NIH. It's a development of tools and technologies to bridge across scales of biological systems or organization. And when you're doing that, access to all kinds of data and leveraging that data in workflows has been one of our innovations. So what scales are we talking about? Both spatially and temporally. We are going from molecular scale to the organ scale, and you see there's a lot of interaction points or gap points between these scales. And one of the goals is how do you then make these different scales interact and bring multi-scale modeling into these workflows. And while doing that, take advantage of a number of data sources. Now, this is not going to happen only by modeling, but can you bring data from things like electron microscopes and synchrotrons and things like that, and take advantage of it, organize the data, and make it accessible as data enriched by metadata and metrics that I was mentioning before, and take advantage of it in these workflows. So we see it in all kinds of different scenarios in biomedical space.
Thank you for attending our InfoCast. From all of us at HGST, have a great day.